Hello, Math 7. We are here doing our Remote Learning 1 video that correlates directly with your Remote Learning number 1 DeltaMath assignment. This assignment is to supplement the weeks starting next week through May 1st, since we are not going back to school. Those packets are not enough material to supplement for what we would have been doing in fourth quarter. And what we left off on was probability. So that's what this assignment starts off on, is probability. And if you remember correctly, we left kind of talking about something like this, where we saw this number line as all of the probabilities that we're talking about. So a probability is between the numbers 0 and 1, where 0 means it's impossible. Right? This is a 0% chance something will happen. And 1 means it's certain, or 100% chance that something will happen. 0.5, right in the middle, is a 50% chance of something happening, which is equally likely as unlikely. 0.25 meant it was kind of likely, right? This is a 25% chance something will happen. This is like, for example, when we had a spinner and we said, what's the probability that you spin a 2? Well, it's 1 out of 4, or 0.25, or 25% chance this will happen. That's kind of likely, not impossible. And something that's pretty likely was like, say this was green, 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 blue. What is the probability that you'll spin a green? 75%, or 3 out of 4. This is pretty likely, but not for sure. Okay. All right, so that is what we left off on. This DeltaMath assignment does require you to put all your probabilities in as a decimal or a fraction. I tried to do it as a percent on one of the questions, and it counted it wrong. So I would just stick with decimals and fractions. And not percentages. I'm not sure why that is, but that's okay. All right, so we're going to dive into our first area here, and that's questions that ask you to find the probability of something, but it uses the words or, and. And we'll kind of tell you what that means as we go through the question. So this first question says, there's a spinner with 14 equal areas, numbered 1 through 14. If the spinner is spun one time, what is the probability that the result is a multiple of 3 and a multiple of 2? So we have to pay very close attention to that word, and, because it means that both things are happening. Okay. All right, so I'm going to draw a spinner. And it needs to have 14 equal areas, which means there should be 7. Hopefully those are a good size. Trying to make it kind of even. Not too bad. Do you remember my fantastic drawing skills? Okay, there's my spinner. It has 14 equal sections, numbered 1 through 14. 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, it says, if the spinner is spun one time, what is the probability that the result is a multiple of 3 and a multiple of 2? So let's go through with a different color marker and just kind of color in the things that are a multiple of 3. So that's 3, 6, 9, 12. That's it. Those things are a multiple of 3. And then it says a multiple of 2. So let's use another marker. I'm using blue. Okay, so this one. And 4, right? 2, 4, 6, 8, 10, and 12. Oh, and 14. So my green are all the multiples of 3, and the blue are all the multiples of 2, but the question's asking us, what's the probability that it'll be a multiple of 3 and a multiple of 2? So I need to be looking at the areas that are both green and blue, and that's 6 and 12. So if I spin right here, if I spin a spinner, what are the chances it's going to land on this one or this one? Because that's what we're looking at. Either that's 2 out of 14. So our answer would be 2 over 14. This is not simplified. This is the same thing as 1 over 7. Okay, and that's what we would put in here. 1 over 7. Okay. All right, so then it goes through and says multiples of 3 are 3, 6, 9, 12. Multiples of 2 are all of those even numbers. Multiples of 3 and 2 are 6 and 12. So the number of accepted values are 2, number of possible values are 14, and that's what we did. We simplified 2 over 14 or 1 over 7. Okay, now I want to look at a problem that's not an and question. I want to look at an or question. All right, so here's one. In certain Algebra 2 class of 29 students, 8 of them play basketball, 16 of them play baseball. There are 11 students who play neither. What's the probability that a student chosen randomly from the class plays basketball or baseball? All right, so let's say I walk into our class and I say, who in here plays basketball? And I have like, I don't know, a certain amount of people, Zion raised their hand and a couple of boys raise their hand and they all play basketball. Okay. So let's say there's just some people that do that. And then I say, all right, well, who in here plays baseball? And then I have some new people raise their hand, but some of those other people that play basketball too also raised their hand. So a couple of people play basketball and baseball, and that's okay. Because when I asked, I was just seeing who in general plays, not who plays both. It doesn't matter. All right, but if I wanted to say who raised their hand, who plays basketball or baseball, then all of those people that raised their hand the first time and all of those people that raised their hand the second time would raise their hands. And the people that wouldn't have their hand up anymore would be the people that don't play either of those sports, correct? So who doesn't play a sport in this class? Well, 29 students, right? 8 of them play basketball, 16 of them play baseball, 11 students play neither. So that means 29 minus 11 students should be our answer. All right, and if you want to think about this another way, we can kind of like make a little table. So let's say people who play basketball, people who play baseball, people who don't play baseball, people who don't play basketball, and the totals of those people. All right, so how many people are in the class? There's 29. I told us that. Okay, 8 of them play basketball. Okay, basketball. Total people that play basketball, 8. Sorry if you can't see that. There we go. 16 of them play baseball. Okay, baseball. The total amount of people that play baseball, 16. Notice how I'm not putting that like here somewhere because I don't really know specifically if they also play basketball or don't. Okay, and then 11 students play neither. All right, so they don't play baseball and they don't play basketball. So 11 students play neither. Okay, but I know that there has to be 29 students total in the class, right? So this 16 plus something here should add up to 29. So this number must be 13. And these two numbers must add up to 13. This is a total column, total row. So these things must add up to 13. What plus 11 is 13? 2. All right, sorry for the glare. Okay, well, these two numbers must add up to 8. So what's this have to be? 6. And these two numbers must add up to 16. So that has to be 10. And the total of these two numbers is 22. 21. And thankfully, 8 plus 21 is 29. So all of our rows and columns added up correctly. Now I can definitely see, and I'll use a different color marker, that 11 people don't play baseball or basketball. Okay, they don't play that. So what's the probability that a student chosen randomly plays basketball or baseball? Well, it's all of these people. It's everyone that doesn't play. right? This person, these people play baseball but not basketball. That's okay. They would raise their hand if I asked. These people play baseball and basketball. They would have raised their hand at some point. These people don't play baseball, but they do play basketball. They would have raised their hand at some point. So this total is what we're looking for. So 10 plus 6 plus 2, which is 18. So 10 people that play baseball plus 6 people that play both plus 2 people that play basketball, that's 18 students. It also happens to be our total number of students minus how many people don't play a sport. All right, so 18. But 18 is not our answer because 18 is not a number between 0 and 1, right? 18 out of 29 is our answer because there's 29 students in the class. Okay, submit. Yes, good. So now we see the difference between and or, okay? Because if I had asked what is the probability that I pull a student randomly from the class and they play basketball and baseball, well, then my answer would have been this, because they play basketball and baseball. But I looked for or. That was everybody that didn't play a sport, right? If I asked what is the probability that I spin a multiple of 2 or a multiple of 3, well, that would have been all of these things. Because these are all multiples of 2 and 3. So if I wanted to spin a multiple of 2 or 3, that covers a lot more ground than just spinning 2 and 3. So there's a big difference between and or. All right. And then you can, of course, message me if you have a specific question. You know, sometimes these little wordy questions get a little confusing. So, you know, just let me know. There's always an easier way to think about stuff. And for some reason, these probability questions can trip some people up. It's some people's cup of tea and some other people's not cup of tea. All right. So our next question is probability from a two-way table. All right. So this time we have the table made for us already. Okay. Sorry, I had a phone call there. All right. So in a class of students, the following data table summarizes the gender of the students and whether they have an A in the class. What is the probability the student chosen randomly from the class has an A? All right, so we look here. So these are girls that have an A. These are boys that have an A. These are girls that don't have an A, and these are boys that don't have an A. All right, so it's asking us the probability the student chosen randomly does have an A. So we only want to look at these two people, or these two groups of people. How many people do have an A? 6 plus 9. That's 15 people. So I'll say 6 plus 9 out of how many people are in the class total? So that's 6 plus 9 plus 3 plus 4. All right, so over here I have the students that do have an A, and these are the students that are in the class. So that's 15 out of, let's say 15, 18, 22. So 15 out of 22 students have an A. Okay. And they did the same thing. They made like little totals, right? So there's 15 here, 7 here. 6 plus 3 is 9. 9 plus 4 is 13. And then just added these up. But, I mean, you didn't have to go through all that. You could have just done it, you know, in your head. But there we go. So I guess the moral of the story here is to put, you know, our favorable outcome, which is what we're looking for in the numerator, and all of the outcomes in the denominator. So 15 people had an A. There were 22 people in the class. So what's the probability that I choose somebody randomly that has an A? Well, 15 out of 22. All right. And finally, compound probability. Now, this is something I want to dive into without questions on DeltaMath first. So I'm going to go to this page, and we're going to do a short little lesson on this first. Okay. Compound probability is like looking at the probability of more than one thing happening at the same time, or like one right after the other. So this is a neat little example talking about passwords. So it says, which password requirement is most secure? Explain your reasoning and include the number of different passwords that are possible for each requirement. So the password must have 4 digits, okay? So here we go. our password must have 4 digits. All right, 4-digit password. 1, 2, 3, 4. Now, a digit, that's a number, right? What are the possible numbers that could go here? Well, 0, 1, 2, 3, 4, all the way down to 9, right? And actually, I'll just write them out so you can make sure you see them all. Oh, and I put 10. That's silly. Okay. Because these are 1 digits, right? This is 1 digit, 1 digit. I can't put 10 here because that's 2 digits. Okay. All right, so these are all the possible things. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? There's 10 possible ways for this number to be. Okay, so there's 10 ways I could pick my first number. All right, well, what could my second number be? Well, it could be any of those things. Again, it could be any of those numbers. That's okay. I could have 0, 0. Like, that's allowed. I mean, it's not smart. It's not normal, but we could. So there's 10 different ways to choose a second number. How many ways are there to choose this number? Again, the same. There's 10 different ways to choose this number. And this final digit is no different. There's 10 different ways to choose that number. So how many different combinations are there? Ten times 10 times 10 times 10. There are 10,000 different ways for this password to be created. That's a lot. But you'll see that it might not be that much. Okay, so the password must have 5 digits. All right, so if a password must have 5 digits, then it's just a little bit different than this question. Now we have 10 ways to choose the first, 10 ways to choose the second, 10 ways to choose the third, 10 ways to choose the fourth, and 10 ways to choose the fifth. That's going to be 1 more times 10. There's 100,000 ways to make this password. Okay. The password must have 6 letters. All right, so let's think about this one. I'll put it over here. 6 letters. 1, 2, 3, 4, 5, 6. All right, well, what could I put here? You know, A, B, C, D, all the way down to Z, right? It must have 6 letters. And it does not specify capital or lowercase. Let's make sure. I think we're just thinking caps because it looks like they do all caps there. All right, so that's 26, right? There's 26 different ways. And then there's 26 different ways to choose this one. And 26 different ways to choose this one. And 26 different ways to choose this one. And again, 26 ways. And again, 26 ways. Because my password could be A. It could be 6 A's in a row. It's not normal, but we could. All right, and so we figure out the probability of that by doing 26 times 26 times 26 6 times, because it's a 6-digit password. All right, that's a lot of different combinations. An easier way to do this would be 26 to the 6th power. Okay, so 3, 0, 8, 9, 1, 5, 7, 7, 6. Woo! Okay. So far, the 6-letter password seems to be a lot more secure. Why is that? Because there's a lot more different combinations. It would take a lot longer for a computer or a person to hack into this password. All right. Now, this last one says the password must have 8 digits or letters. All right. So this is 8 digits or letters. So 1, 2, 3, 4, 5, 6, 7, 8. Already we know it's going to be more secure because it's longer. But what are the possible things that I could put here? I could put 0, 1, 7, 9, or Z, L, K, B. I could put any letter or number. So there's 26 letters and 10 numbers I could choose to put here. That's 36 different things that I could put in this spot. That's all the numbers from 0 down to 9 and all of the letters from A to Z. Okay, 10 numbers, 26 letters. All right, and I could do the same thing here, and here, and here, and here, and here, and here, and here. All right, because it says letters or numbers. All right, and that is 36 to the 8th power. All right, and as we can see, my calculator can't even show that to me because it's so big. It's 2.8 times 10 to the 12th power. 2.8 times 10 to the 12th power, or in other words, 2.8, and we move the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times. This is an introduction to scientific notation for you for next year in 8th grade. All right, that's how big this number is. That's how many different combinations. So this is a very secure password. Okay. All right, and then let's go in to see what it says. The set of all possible outcomes of one or more event is called the sample space. So like the password 1, 2, 3, 4 is part of our sample space. It is a password we could have made. All right, you can use tables and diagrams to find these sample space. Now, I think this is super important, finding a sample space. This is something that would probably be asked by you on the air test if you were supposed to take it this year. So let's think about, you randomly choose a crust and a style of pizza, find the sample space. How many different pizzas are possible? All right, well, let's say I could choose thin or stuffed crust. I could choose Hawaiian, Mexican, pepperoni, veggie, Hawaiian, and Mexican, pepperoni, veggie, right? These are my style options, and these are my crust options. So I could get a thin crust Hawaiian, or a thin crust Mexican, or a thin crust pepperoni, or I could get a stuffed crust Hawaiian, or stuffed crust Mexican, or stuffed crust pepperoni, blah, blah, blah. How many different outcomes are in my sample space? 8. You see that? There's 1, 2, 3, 4, 5, 6, 7, 8 different options. In other words, there's 2 times 4 different options. This is something called the fundamental counting principle. Another way to find the total number of possible outcomes is to use the fundamental counting principle. For example, say you have 4 pairs of shoes in your closet and 8 sweaters and 3 pants. Well, how many different outfit combinations do you have? 4 times 3 times 8. You wouldn't have to go through and match them all up. You could just multiply how many options there are, and that's kind of what this says. An event M has M possible outcomes. An event N has N possible outcomes. The total number of outcomes of event M followed by event N is M times N. That's a lot of words for really just saying what we just did, right? There's 2 different crust options, 4 different style options. How many options are there to get your pizza? 2 times 4, or 8. All right, so we can think of it kind of like this. Let's do this. This is a good question. Find the total number of possible outcomes of rolling a number cube and flipping a coin. Okay, so we can roll this number cube. It's a 6-sided die. So the options, my outcomes are 1, 2, 3, 4, 5, 6, right here. And I flip a coin, my options are heads or tails. So either I roll a 1 and I flip a heads, or I roll a 2 and I flip a heads, or I roll a 3 and I flip head, or I could roll a 4 and flip tails, or I could roll a 5 and flip tails. You see all of my options here? How many options are there? There's 12 different options. In other words, 6 outcomes times 2 outcomes, 12. Okay, and it's just a lot faster than having to make this whole diagram or think about what are the different combinations that could happen when I do 2 things at the same time. Okay, so knowing that, I think I'm going to move down to compound. Okay, this is what we're supposed to talk about, compound probability. A compound event consists of 2 or more events. Okay, so as with the single event, the probability of a compound event is the ratio of the number of favorable outcomes to the number of possible outcomes. That's kind of what you were saying, and just like 5 people play baseball out of 10 people, what's the probability somebody plays baseball? 5 out of 10. Okay, let's see. Finds the probability of a compound event. We already did something like that in the DeltaMath question. Okay, this is a good question. You flip 3 nickels. What's the probability of flipping 2 heads and 1 tails? Okay, so this is 2 things happening. We need to flip 2 heads and 1 tails. Use a tree diagram to find the sample space. So we see this tree diagram over here. It's called a tree diagram because obviously it looks like it's kind of branching out. So I flipped 3 nickels, right? So I flipped the first nickel, and either it's a tails or a heads. Now, say I flipped a tails. Now I flipped the second nickel. Say it's a tails or a heads. If it was tails, then the next time I could choose tails or heads. This combination is tails, tails. This combination is tails, tails, heads. And the same thing, if I had flipped a head first on the first nickel, the next nickel I could flip heads or I could flip tails. That time I could flip heads or I could flip tails. This combination, we just follow along the branches. That's heads, tails, tails. And they have that kind of labeled here. And that's what these like HT thing is. All right, so what's the probability of flipping 2 heads and 1 tails? Well, that's everywhere we see 2 H's and 1 T. That's here, here, and here. That's 3 out of how many different combinations were there? 1, 2, 3, 4, 5, 6, 8. Okay, so that's 3 out of 8. And they put it as a percentage. All right, so knowing that, let's go back to our DeltaMath assignment and look at compound probability. All right, so a bag contains 6 red marbles, 7 blue marbles, and 8 green marbles. And that's just the same color of markers I have. That's awesome. So there's 6 red marbles, 7 blue marbles. I'm writing this on my board right now. And 8 green marbles. If 3 marbles are drawn out of the bag, what is the exact probability that all 3 marbles drawn will be blue? Okay, now it says exact probability because it wants you to use a fraction. If we used a decimal, we might have to round, and that's not exact. So that's why exact is like italicized like that, because it wants you to use a fraction. All right, but first of all, in order to make our fraction, our probability, we need a denominator. And the denominator means all of the possible outcomes, right? And, well, we'll do that in a second. But that's what should go in our denominator. Okay, so there's 6 red, 7 blue, 8 green. All right, and it says, what's the probability that all 3 marbles drawn will be blue? Well, what's the probability that I draw a blue one first at all? There's 7 blue, right? Out of how many marbles? So this is like my first draw. Draw 1. 7 blue out of 6 plus 7 plus 8 marbles. That's 21. So 7 blue marbles out of 21 marbles. That's the chance that I'll draw a blue one on the first draw. What about on the second draw? Well, if I did draw a blue one, then there's 1 less blue marble, right? Now I have 6 out of how many marbles? Well, there's 1 less marble in the bag. So now I have a 6 out of 20 chance of drawing a blue marble. And on the third draw, well, if I did draw a blue one, then there's 1 less blue marble in the bag. So now I have a chance of pulling 5 out of how many marbles? Well, if there's 1 less marble in the bag, now there's 19 marbles in the bag. All right. And this is the definition of compound probability right here. To find the probability of multiple events happening, you have to multiply the probability of all the events happening. All right, so let's do that. We have to do this times this times this. All right, and I'm going to make my life a little easier and simplify these fractions first. 7 out of 21 is the same thing as 1 over 3. 6 over 20 is the same thing as 3 over 10. And 5 over 19 is already in simplest form. So let's multiply the numerators first. 1 times 3 times 5 is 15. And 3 times 10 times 19, let's do that. 3 times 10 times 19 is 570. This number looks like it could still be simplified. I'm going to go ahead and divide this number by 5. 114. So divide by 5, divide by 5. I just did that on my calculator. It said 570 divided by 5 is 114. 15 divided by 5 is 3. This can still be simplified. Do you remember this trick I showed you a long time ago? 114. What's 1 plus 1 plus 4? 6. Is 6 divisible by 3? Yes. So is 114. So 114 divided by 3 is 38. So 3 over 114 is the same thing as 1 over 38. All right. That's our exact probability. Submit. Okay. So they did the same thing. They multiplied all of their numbers here. They kept big numbers, and that's why they got these huge numbers, which is why what we did was a little easier. But again, it just said number of marbles total. There's 21. Probability of drawing a blue on the first draw is 7 out of 21. On the second draw, there's 1 less blue marble, so now there's 6 marbles, and there's 1 less marble total. So 6 out of 20 marbles. It's a chance of drawing a blue one now. On the third draw, well, there's 1 less blue marble, so now there's only 5 in the bag. And there's 1 less marble in general, so there's only 19 marbles in the bag. So that's the probability of drawing a blue one on the third draw. The probability that they'll all happen is the product of all their probabilities. That's like the definition of compound probability. So that's like the one thing I really want you to take away from this. For instance, we can even take it down a notch and think about just like flipping a coin. Right? Let's talk about flipping a coin. What's the probability that I flip a heads? Or let's talk about flipping a coin twice. Flip coin twice. Well, I could flip a heads first, and then I could flip a heads again. I could flip a heads first and then flip a tails. I could flip a tails first and then flip a heads. Or I could flip a tails first and then flip a tails. So what's the probability of flipping a head twice? 1 out of 4. What's the probability of flipping a tails twice? 1 out of 4. What's the probability of all of these things happening? 1 out of 4. And the reason why that is because what's the probability of flipping a heads in general? 1 out of 2, right? Flipping a coin, there's a 50% chance it'll be a heads and 50% chance it'll be tails, right? 1 out of 2 options. Well, then and if I want to do it again, same thing. Probability of 1 out of 2. When I multiply those things together, I get 1 over 4. So the chance of the events happening here are 1 over 4. We just multiplied the two probabilities together. Okay. All right. I think that is the gist of it, and look forward to another video to help you with the remote learning number 2 assignment. And I hope you guys are having, a lot of sleep and whatnot, and let me know if you have any questions. I did post about office hours on Schoology. I was in my warm-up, watch this first YouTube video. I might also just post other random fun math videos for you guys in case you're crazy bored. But other than that, have a good day, and I will see you later.